Okay, good morning, everyone, and welcome to the IFIMAC+ICMM joint seminar series on condensed matter. So it is my pleasure to introduce our speaker today, Anna Böhmer. Anna, she's an experimental researcher on superconductivity and other correlated electronic phases. She uses different techniques from the crystal growth of the materials to the experimental characterization using transport and other thermodynamic properties. Anna completed a double degree program in physics at the Karlsruhe Institute of Technology and also the École Polytechnique in Paris. Then in 2014, she obtained the PhD in Karlsruhe under the supervision of Professor Lunaisen, where she studied the Nematic order in iron-based superconductors. Then she moved to Ames, where she made a postdoctoral research, where she was a postdoctoral research associate in the group of Paul Canfield for 3 years. There she worked on the discovery and design of novel materials and ground states. Since 2017, and also in the next 2 years, she is a Helmholtz Young Investigator Group Leader at the Karlsruhe Institute of Technology, where she is making nice contribution on the strain tuning of correlated electronic phases. Starting this year, she obtained a new position as Professor for Experimental Physics at Ruhr University Bochum. So as I said, it is a pleasure to have Anna here. Today she is going to tell us about iron-based superconductors, materials, magnetism, and tuning methods. So before giving the floor to Anna, let me remind you that during the talk, the microphones will be muted, but you can ask questions by writing them in the chat. At the end of the talk, there will be more time for questions, so you can also use the chat or raise your hand, and I will unmute your microphone so you can ask the question yourself. With this, I finish, and thank you all for coming. And Anna, the stage is yours.
Hey, so hello, good afternoon or good day, everyone. Thank you, Isabel, for the nice introduction and also for the invitation to the seminar. It's a pleasure. I thought I would show you a few interesting results on the material class that I've been working on for many years now on the iron-based superconductors, what kind of materials we're working on. Then one of their interesting properties is their magnetism, and we will see how these are interesting magnetic materials, and tuning methods, how to change their properties, change their magnetism. Tuning, I think, is a nice word. It really comes from the radio technology when you tune a frequency. So that's my symbol for tuning, but we use it frequently in this field to mean change a material. As Isabel said, I've been at Karlsruhe Institute of Technology for quite some time. This is where most of this work has been done. And now I'm at the Chair for Experimental Physics 4 in Bochum. So basically here. Experimental Physics 4 is, well, is the name of the institute. It's also on the 4th floor. This work has not been done alone. And here I list collaborators. There's a large group at the Karlsruhe Institute of Technology. There's another large group where I did my postdoc at the Ames lab under Paul Canfield's group. There's also the scattering group there. Alan Goldman is the leader. NMR group, another low temperature group, and external collaborators all over the world, be it in the US, in Vienna, in Kyoto, in Zurich, and also had some very nice work with Hermann. I'll mention it as well. So let's start general. What do we study? One thing we really like to study is order. Order in general terms. If we look at the crystal, at the material, the crystalline material, what we have is atomic order. The atoms or the ions are in specific places. And because in this case, the atoms are arranged in this cube structure, the crystal looks like little cubes. So we can really see it. This is a millimeter scale. We can see how the atoms are arranged there. There are other kinds of order, and one of them is magnetic order. That's your fridge magnet, for example. What we have here is the spins on the sides of these electrons. They are ordered. They say in the fridge magnet all point in the same direction. But there could be other kinds of magnetic order. One famous one is antiferromagnet, where they are alternating up and down, but in an ordered fashion. What happens if we destroy order? We know that from daily experience. We can melt a crystal. We can also heat up the fridge magnet. At some point, it will lose magnetic order. The spins will be disordered from like thermal excitations. That's a phase transition. And well, that's something we understand. And I really like to show this graph. It, I think, tells us something about physicists. It's from Saturday Morning Breakfast serial comics, a nice site. It's how academics call something boring by discipline. So philosophers, that's elementary when they see something that's elementary, that's boring. For mathematicians, that's trivial. And physicists, what they say is that makes sense. Well, you see that physicists use plain language, but you also see, or what our understanding is, what we understand, that's boring. We want to find new physics, new materials, new phases, also beyond standard model, particle physics. That's what excites us. And let's look at one of these things that we don't quite understand yet. That is when magnetism is destroyed. We just had that. If you increase temperature, say, then you go from an ordered magnet to a disordered phase. But what happens if you change some other parameter, say pressure on a material or chemical composition? Then this temperature where you destroy the magnetism can change, can decrease. And it can, and this thing that you change, that's an example of a tuning parameter. So we tune the phase transition temperature here. You can tune it further and we can tune it to 0. And when we do that, what we find on the other side, well, you typically find normal metal. And the point that's interesting is here. Here the material doesn't really know what it should be. It should be a magnet, should it be not? And usually it decides to do something else completely. Here's where new phases can emerge. And one of these could be or is superconductivity. And this is one of the first cases where such behavior was observed. What we see here is an antiferromagnet, cerium palladium 2 silicon 2. And if you apply pressure to it, physical pressure, then this transition temperature gets suppressed, just as we said. And we see a dome of a new phase. And this phase is a superconducting phase. This is the electrical resistance. It goes to 0. So here we're tuning with hydrostatic pressure. And now I want to tell you a little bit about what is superconductivity. Superconductivity was discovered in 1911, so more than 100 years ago. And this is the original data from Heike Kammerling-Onnes, electrical resistance of mercury, which on cooling below 4 Kelvin drops from some finite value to exactly 0, or to immeasurably small in his case, but it's exactly 0, that's the point. So superconductivity. This is used nowadays. It's used, for example, in magnetic resonance imaging, medical imaging. What we need for that is a high magnetic field. To get a high magnetic field, we need a large current. If we drive that through a superconductor, that's what we get. If we would drive that through a normal metal, we would not only get a large field, we would also get a lot of heat because of dissipation resistance. And then an MRI would not be an MRI, it would be a toaster. So it's the superconductivity that makes the difference. This is a famous plot of the history of superconductivity, a way to see it. What we plot here is a function of the year of the discovery, the temperature below which a certain material is superconducting. And you see over 100 years, there have been a lot more materials found, but this is the highest TC ones and highest critical temperature ones. And there is an increase, but it's small. To this plot, you can add milestones of research, the discovery of the zero resistance. There's an effect called Meissner effect about the behavior of a superconductor in a magnetic field. There is a theory that explains this effect. It's actually a triumph of condensed matter theory, but you can see it did not help us getting higher TC materials. So this just continues. over this period, and with all of these materials in mind, a couple of rules have been established for how to find a high temperature, a good superconductor. And they are the famous Böhmer rules. So in a short version, they say, try to look for superconductivity in a high symmetry material, ideally a cubic material that's the same along all directions. High electronic density of states also helps. So lots of electrons at the Fermi surface. Lots of states for electrons at the Fermi surface. Materials that contain oxygen are not a good idea. Materials that are magnetic are not a good idea. Insulators are not a good idea. And there's an apocryphal one, maybe. It's don't listen to the theorists, they cannot predict it. So that was established, and that helped to find a lot of these materials. And then in '86, there was a discovery. That was the cuprate high temperature superconductors. And you can see this enormous increase in critical temperatures. So now suddenly we have a superconductivity that's superconducting below 130 Kelvin or more. That's huge. That was a revolution. What happened here? Well, if you look to Böhmer rules, we've basically violated them. These are not cubic materials. They are very much two-dimensional, basically the opposite of cubic. There is a very low electronic density of states. They are oxides. Here's an example. They are magnets, at least in their undoped state, but there's magnetism there. They are almost insulators. The only rule that's still valid is, well, the theorists couldn't predict that. So that one still works. So after the discovery of the cuprates, another class of high temperature superconductors is these iron-based superconductors. That's the one that I will talk about later in this talk. You can see the critical temperatures are not quite as high, but as you will see, they are also very fascinating. And one aspect that's fascinating is their phase diagrams. So this is a phase diagram, a temperature and a tuning parameter to the right. And what you see is a superconducting range. That's the green part here. It's the green-yellow part here. What they have in common, there's something else around here or here. So if we look at, and if we think about the introduction, that looks similar. So our new paradigm is, well, we want to look for magnetic phases or other phases that are suppressed. And around the point where they're suppressed, maybe that's where we find our interesting superconductor. That is a fruitful way. But it's not the only way. So now I have to change my scale on my history plot. And that was only a few years back. Superconductivity was found at, well, almost room temperature. It's not quite room temperature, but this is outside temperature in winter in Siberia, for example. The drawback is this is superconducting at only 200 gigapascal of pressure, so that's very far from atmosphere. So applications are still far, but fundamentally we have found a really high temperature superconductor here and these high-res materials. What we go back to our rules now, we know these rules, well, they didn't work for the 1986 discovery. For the 2015 discovery, even that one is violated. The theorists did predict it, and it was found experimentally only later. So the theorists said, look at this at high pressure. And high superconductivity, temperature superconductivity was found. So with this, let me come to the class of superconductors I have been working on, the iron-based superconductors. And one thing that's really fascinating about them is we have a lot of them. We have different materials. There's some abbreviations here. They come in different chemical structures. What they have in common is iron, in red here, and then typically arsenic, sometimes phosphorus around them in layers. But we can use many other elements as well. So there's a good part of the periodic table that can be taken, built according to these structures, and every time we find a superconductor. That's quite amazing. So there's a lot of tuning parameters, even a lot of chemical tuning parameters we can play with. And let's look at the typical phase diagram here. So again, I have temperature, and now I have chemical composition here as my tuning parameter. The material specifically is barium, iron 2, arsenic 2, and then a little bit of phosphorus in there. What we find is an antiferromagnetic phase and a superconducting dome, very similar to that suppression of magnetism and a new phase emerging, as in the introduction. So the question here is, and the question that we are very much interested in, what is this phase that is suppressed to get the superconductivity? And here we have a magnetic phase, we have an antiferromagnetic phase, which is a little bit special. What we find is the magnetic moments, which are disordered at high temperature, they point in any direction. They order in this way that they are parallel along this one stripe, and then antiparallel to the next ones. So we have a stripe type antiferromagnet. So basically a ferromagnetic direction and an alternating direction here. That has interesting consequences, which I will explain in a bit. One of these consequences, as a preview, is magnetoelastic coupling. So now we couple the magnetism to an elastic property. So if we go from this state to this one, we go from something that's a square here, the material itself, it's called tetragonal, but the iron lattice is just square, to something that is no longer square, because this direction is just different from this one. So just by symmetry, this cannot be a square, a perfect square at least. If we measure this, we find it's not a perfect square. So here is function of temperature. We look at the magnetic, basically how much the magnetic order there is in blue, and how much this deviates from being square in red, and that just goes hand in hand. So we find a strong coupling between this sort of antiferromagnetism to a structural distortion from square. This goes with what's called an emergent order parameter, and that's going to be at the end of my talk. I hope I can explain this interesting concept of solid-state physics. But after a decade of research now, this was discovered in 2008, I think it's time to take a bird's eye view and to see what's there. What can we understand by looking at many materials, many properties? And what I will find and what I will show you is different sorts of magnetic order, a couple of different phase diagrams and different their particularities, and a couple of tuning parameters. We had chemical composition. We already talked about hydrostatic pressure, but there are a few more. But when we do our experimental research, and this is really data that I've taken, is one question is, how do we see superconductivity? How do we measure it? And we do nothing else than commonly honest, and we measure electrical resistance. We put 4 contacts on a sample, we measure the voltage we applied to the sample, and the voltage on a sample, the current, and we find zero electrical resistance below a certain temperature. We also measure magnetic susceptibility. That's this Meissner effect that I've briefly mentioned. It's the property of a superconductor to be a perfect diamagnet. But, there's machines to measure it. You need to understand better what they do. But what you find in the end is a diamagnet here, below a certain temperature. And there's other things to measure on a superconductor. These two, that's just the definition of superconductivity. These other things, they tell us something more. One of them is the sample length change on going through a superconducting transition. So here, what I plot is as a function of temperature, the length change of my sample. So like a piece of copper that shrinks when you cool it and expands when you heat it up. Any sample will change length when you change temperature. But when you go through a superconducting transition, and that one is here, this length change will change. So really you can see the fact that the sample, the electrons in the crystal go superconducting, lose the electrical resistance in the sample length as a function of temperature. That's what we see here. If you think of this is quite amazing. Another property is the specific heat. So how many Kelvin, how many degrees a sample heats up if you put a certain amount of energy into it. And there is a huge change also at the superconducting transition. This has to do with electronic order and the entropy that's lost there. It's also an important feature of a superconductor, and we can learn something from how large this change is. And let's see what we can learn from this. In a bit. First, I had my measurement setup, or one of my measurement setups, the one that I like most actually. It's a capacitance dilatometer. This is something to measure length changes with high resolution. The principle is easy. We have a plate type capacitor. So the capacitance, you learned it in elementary physics, depends on the distance between two capacitor plates. The magic and the trick is to couple the distance between these two capacitor plates, they are found here, to the length of a sample. And if you do that, all you need to do is read out the capacitance to get the length change of the sample. And we can do that with very high resolution. We can see length changes of fractions of angstrom. Just to remember, just to find pictures for how much that is, it means that if our 1 centimeter sized sample changes by 1/10 of the diameter of a hydrogen atom, that's 0.1 angstrom. That's a change that can be seen. Or try to find macroscopic examples. It's as if the height of this highest building in the world in Abu Dhabi changes by the diameter of spider silk. That's a length change that can be seen. And that's something it can tell us about this superconducting properties. And what is that? One thing we can learn is uniaxial pressure effects. So this is a basic thermodynamics. You might have seen that before. What it tells us, the relations are quite famous. One is Clausius-Clapeyron. What you say is that the pressure derivative of a certain temperature is given by the length change of a sample at that temperature, or the volume change divided by the entropy change. You can see that with ice. It's quite intuitive. Well, ice has a larger volume than water. So if you compress ice, you'll melt it. It wants to be water. It does not want to be ice anymore. That's what this relation means. You can do it too for so-called second order phase transitions. When length changes, where there is rather kinks in the length or jumps in the derivative of the length, that's this alpha, and then it's called Ehrenfest relation. Here are some examples. At this transition, the length or the volume increases suddenly, the entropy decreases suddenly. I take the ratio of the size of these anomalies and I get the pressure derivative. Here, that's a superconducting transition actually. This expansivity increases and the specific heat increases. Let me just go back to show you where this comes from. So this was the length at a superconducting phase transition. It doesn't jump, it has a kink. Temperature derivative of this will be a sudden change. This is very steep, this is very flat. And that's exactly what goes in here. That's exactly this. So if we do that, what can we learn? This is what we learned for one of these iron-based materials. What I show here in terms of arrows is over the phase diagram. This is a magnetic phase, this is a superconducting phase, there's a couple of more phases here. What we learn is at a uniaxial pressure in the plane, symbolized here, this transition temperature will go down by this much. And this one will go down by this much. This one will go up. So summarizing this way. On the other hand, we did similar measurements, but now for z-axis direction. What we learned there is if you compress the material along this other axis, this temperature will go up, this will go down, this will go up. So there's a sign change here. Everything's opposite. So what we can conclude is that the best tuning parameter is neither this pressure nor that pressure, but it's the difference of the two, or the ratio of C over A, the ratio of this length to this length. That's the best tuning parameter. And we have used it to change the C over A ratio externally, like voluntarily. You need to play a few tricks. That's not so easy. One trick that we did is we have a sample and we put it on a substrate. Substrate is glass here. It's really just a piece of a microscope slide cover glass. And we know this thermal expansion of sample and glass. It was measured. So the glass, that's a regular curved thermal expansion. You cool it down from room temperature, it shrinks by a little bit, fraction of a percent. Our sample, it turns out, actually wants to expand on cooling. It's negative thermal expansion. That happens. But this also means that if we have a sample on glass, it wants to expand, but it can't because we fixed it to it. So what we are really doing is we compress it in the plane. The z-axis, the other dimension up here, it's free. So if we compress something that doesn't want to do it, it will expand in the other direction. So we are really changing the C/A ratio here. And what happened? What we saw is, okay, this is basically a sample length, but measured using X-ray diffraction. What we see is a transition as function of temperature from a single peak to a double peak, or from a single lattice constant to a double lattice constant. What this means is there was a structural phase transition. Actually here, this was a square and now it's a rectangular lattice. That's what we see here. We also used a different technique, that's a Mössbauer spectroscopy. Don't really need to understand it. It means, well, we see two very different spectra for a free sample compared to the sample on the substrate here. The sample on the substrate has this complicated spectrum, and it means it's magnetic. There is magnetic order. These moments, they have ordered. And we also measured this magnetic susceptibility, and we find a diamagnet in the sample on the substrate, in the strained sample. So it's a superconductor now, one that wasn't before. So we've tuned the material via the C/A ratio. And if we put all of it together, what we've done is we've manipulated the phase diagram. We went from something like this, turns out, to something like this, using the C/A ratio. I have indicated here a mixed phase, something special that happens. And to me, it was an example that you really need to think carefully. And you should be open to surprises of what happens. And this is, well, thinking about it carefully. If we thought about this carefully, we have a sample on a substrate that is, T stands for tetragonal, like before my transition. But it's strained, it doesn't have the length it wants. And it turns out, instead of staying that way, what it wants to do is, it only goes partially through that phase transition. We have then some regions that are not strained and above, well, without going through the phase transition, and other regions that have gone through that phase transition. By that phase transition, I really mean that structural one here. So we have part of our sample that's here, and a part of our sample that's here, all over the phase diagram, well, all over the mixed phase. And that was, or Hermann saw it together with Anton Fente in STM. So he looked at this and he sees different regions, and these will be these different regions. And if you want to know if it's a superconductor, you can do what's called spectroscopy, and from the spectrum you can see this region is really a superconductor, and the other one is not. You can also look at, is it a square lattice or is it a rectangular lattice? Did it go through the structural phase transition? And then some parts, actually, yes, they did. So what we find here is a really nanometer scale, a very small, interesting domain structure of the same material being in different phases, being in different states. One of it is this orthorhombic, this distorted stripe type antiferromagnetic one, and one is superconducting. And that's quite cool. Maybe we can think of some interesting consequences there. Then, okay, I'm going slow here, but I'll skip a few things. There's just some interesting things to talk about. One thing that we did is we measured the orthorhombic distortion using X-ray diffraction on one hand. That's what I already had. You see a set of peaks and the way they differ, that's how much your lattice differs from square, how much we go rectangular, how much we go in a magnetic state. You can also do that with length changes if you make sure you only measure this direction and not this. That's a short way. We did that. Let's just say we did that. What we find is the orthorhombic distortion, the deviation from square as function of temperature, in a bit of the phase diagram here. When we cool down, we go through the transition, we see the orthorhombic distortion come up. we cool down further, and then we hit superconductivity, and we see the orthorhombic distortion decrease. So here's another effect of superconductivity on the structure. So really the fact that the electrons, they become superconducting, lose resistance, means or has a consequence that my rectangle changes shape. That was seen as well, and what it was seen by other people as well. And what it means is, or what we conclude from this is that the superconductivity and this antiferromagnetic, the striped phase, they compete. Superconductivity doesn't like the distortion, and the distortion doesn't really like superconductivity. So we learned something about the relation between these two phases. A surprising discovery made is we learned something about a new phase, and that's this little red region here. When we did these measurements, what we find is an orthorhombic distortion on cooling comes up and then disappears and then comes back. And that was a discovery, or that was our discovery of a new little phase pocket in our phase diagram here, which was also seen by others. But to us, seeing this curve, it was a real surprise and told about the power of this technique. There is even more phases discovered with this technique, which I will skip here, just in order to come back to an interesting, one of the most interesting effects of this magnetism here. We have discussed so far the transition from this square-like tetragonal magnetically disordered paramagnetic state to this stripe antiferro state. But it turns out, and this really was an experimental discovery at first, there can be an intermediate state. There can be a state that's no longer square, but the magnetic moments, they are still disordered. So if you think about it, it's strange, because we said this is no longer square because of the magnetic order. And now it turns out you can see this being no longer square in a disordered state. What does what does it mean? We worked on it and we found out, but we need a name for that state. And it was named Nematic in analogy to liquid crystal phases. Maybe some of you know liquid crystal phases. There's elongated molecules. They can be totally disordered. They can be crystalline ordered, but they can have an intermediate phase where there's sort of a directional order, but not a perfect order. That is nematic, and that's why we call our state nematic. So in this phase diagram, there's an intermediate nematic state. It turns out this is actually frequent, this intermediate nematic state. I have different materials here, all the orange ones are that. And the question that I've already alluded to is what comes first? Chicken or egg? Is the magnetism causing the distortion, or is the distortion causing magnetism? Well, we talk about fluctuating magnetism, sort of disordered magnetism here. But really what comes first has been discussed a lot. What's the relation? And let me tell you a little bit about what we learned or what we found out. Well, what we used is, it's I think cool, a new way to measure an elastic modulus using a capacitance dilatometer. What we do is we basically apply a force to our crystal. So we go back and forth between here and we measure how much force we need for dilating the crystal by a certain amount. That's called shear modulus, and the technique is actually old. It's a 3-point bending, and that's been used in engineering forever. When you want to build a bridge, you want to test your material, that's what you do. But we do it in our dilatometer. So we apply a little bit of force and we measure length change, how much this bends, with our fraction of angstrom resolution. So we have a new high resolution technique there. Here's examples. We see when we go through our phase diagram, we see how much the sample bends more and more and more and more and more. There is our one transition, and then how it bends a little bit less on the superconducting transition. So there's the competition again, this antagonistic behavior. We did that all over the phase diagram. So you can make fancy color plots out of this data, how much the material is soft. The quantity you can get from this is termed nematic susceptibility. So nematic was our distorted state, the strange orange one that we don't quite understand yet. Susceptibility means how susceptible is the material to get into that state? How easy can you drive the system into this state? And there has been theories on this, and here's I really needed the theory friends, and they actually came to us with their ideas. They say, hey, we can calculate that pneumatic susceptibility. Let's see if you can measure it, and we'll compare. So they calculate it, looks like this. They put a model in it, and then they say, here's a quantity you can measure. It's called T1T, spin lattice relaxation rate. The point is, it can really be measured. On the other hand, this left-hand side I can measure as well. That was my shear modulus. That was my 3-point bending experiment. And the theorist can tell me that there should be a relation between these two. And what we do is we test this relation and we scale the one data on the other, and we find this works. So that theory that starts with magnetic fluctuations, drive pneumaticity, works, can explain this data, and we found evidence for that. And we're quite proud. So let's go back, summarize a bit. And I like summaries in terms of phase diagrams. We've seen this one phase diagram with a structural distorted antiferromagnetic stripe-type phase and superconductivity. We've seen this intermediate phase where my distortion suddenly disappeared, this little pocket. And we've seen this strip of a strange nematic phase that is sort of in between these two. And now it's time to do some systematics. So let me try to explain this, because I think it tells us some cool features about how magnetism can be. We go to theory again. Maybe a few of you are theorists, I don't know. What we want to do is describe magnetic order and how these spins are arranged. And when we take a function with this m, it just means what is the magnetic moment at the position r. We have two amplitudes, two order parameters, and two wave vectors, qx and qy. They are in the lattice. And that's more generally how to describe an antiferromagnetic state in our case. And it turns out you cannot have any values for these two order parameters. They have relations. There's 3 options. And let's go through these 3 options quickly. The first one is our stripe spin density wave that you can see here. It is when it's found when one of these order parameters is 0. So then you have just one of these cosine functions. So cosine along one direction, the other direction is 0. So ferromagnetic in one direction, antiferromagnetic in the other. And depending on which one of these amplitudes is 0, you find the left sort of stripe or the right one. So there's a choice here. I have either this one or that one, and that's exactly my nematic order parameter. You can mathematically, this is 1 or minus 1, if depending on whether you chose the left or the right option. And the name we gave for this, it's a new order, it's a new choice, it's an intertwined order of our magnetism. It's something higher order, something new, something emergent. And we already talked about nematic susceptibility. The point is, and that comes from the theory, is we can find this nematic order parameter. It has to do with the magnetism, even if the magnetism itself is still absent. Or in terms of transition temperatures, we find the nematic and structural transition at a higher temperature, or we can find it at a higher temperature than the magnetic one. And we experimentalists already knew that. We saw it before. We have it in this phase diagram here. We find the nematic before the magnetic. But there is another option. And that one would be both are of same size and either parallel or antiparallel. What would that look like? And you can really make a cartoon trying to add these two terms side per side. So this side, that will just double, the next side will cancel, the next side will double, the next side will cancel. And it turns out the orientation of the moment turns, instead of being in the plane, they come out of the plane. So here my little symbols mean in and out of the screen or into the screen. And that's the choice. The two are parallel. There's a choice, the two are antiparallel. And then we find this sort of pattern. You can really add it now. Now these two add, and the first one would cancel, for example. So there's a new intertwined parameter, a new choice. The choice is, are these two parallel, same sign, or anti-parallel, opposite signs? And you can define a new order parameter. And it turns out this is really difficult to measure. It couples, what it couples to is local charge density, and we haven't seen that yet. And that is really the phase that was found in the little pocket here. That has been measured using neutron scattering, and it was not only neutron scattering, a couple different magnetic probes. It has been found this is the phase that was found here. So we've solved the puzzle. What is this little pocket phase here? It's option 2. And then there was an option 3. Option 3 is if the two order parameters are perpendicular to each other, and was termed spin vortex crystal. Quite a fancy name. Turns out it's a confusing name because there are also superconducting vortices, but this is a magnetic vortex. What does it look like? So I have the two choices already drawn out here. Things are perpendicular to each other, but they have directions. One can be to the right or to the left of the other. We get this sort of pattern. You can also add them. So to the right and to the bottom together gives this corner, to the left and to the bottom gives into the other corner. If you go around one of these plackets, there's sort of a rotation of the magnetic moment, and that's what becomes this magnetic vortex. That's where its name comes from. We have again two choices. The patterns, it's a bit hard to distinguish. It's a shift. So sort of a phase shift, these two choices. We gave another name to this order, hedgehog, because it's some all-in structure. And our intertwined order, our new order parameter, is a choice, well, to the right or to the left, and that's the cross product, a vector product of these two order parameters. It got a name. The question was, can we find it experimentally? And I will cut this a little bit short. We did find it in a new material, a 1144 material. So just for chemists maybe among you, that's structure where we have our familiar iron layers. That's where the magnetic moments lie. We have arsenic around. Then we have, in this case, potassium and calcium alternating. So it's not an alloy. It's a 1144, a quaternary compound. It's a superconducting compound. That was seen quickly. You can just measure resistance again. So here's the resistance curve. Here's the diamagnetism. Here's the specific heat jump that I mentioned. It's a nice superconductor. The question was, can we get it magnetic? Can we get this compound to be magnetic by, well, the same procedure we've used before, chemical substitution, the same things we did before here. And it turns out if we think about it, a promising way would be to substitute the iron with cobalt or nickel. There's a reason for that, but let's just see what it gives. So now I have an empty phase diagram here, temperature and nickel content in my calcium, potassium, iron 4, arsenic 4. And we measured resistance, and we indeed found something. So you see the superconductivity, the zero resistance states, and you see little kinks here. You take the temperature derivative of the curves and you see a transition. You put all of this together, and here's my new phase diagram. We have magnetic order here. And well, then once you see magnetic order, you want to know what is it? How are the moments aligned? What's the pattern? And we find it's really the hedgehog type spin vortex crystal order, our missing option 3, using a couple of different probes that were all in-house. It's a teamwork. That was a good example of how many groups can work together to solve such a puzzle. There's a reason of why we find exactly this complicated structure and exactly this material, and has to do with my intertwined order with these two amplitudes, two order parameters, and the vector product. Maybe well, it's a structural reason. It has to do with these alternating layers. Say so much. So we understood why likely we got this. We are not sure, but we understand why it's more likely to get this option 3 magnetic phase in this material. And with this, I would like to summarize. In these iron-based materials, we have complex magnetism. can be described in this way, and we find three options, three different patterns coming from the same mechanism, same wave vectors. We find the stripe type with the interesting coupling to the structure and the nematicity. We find the spin charge density wave, this alternating one, where moments sometimes cancel. And we found the spin vortex crystal where moments rotate within the plane. Each time there is some new emergent order parameter, which is a concept in this sort of physics, which sometimes we can measure easily and sometimes we can't. And this led us to some tuning using some forces, coupling to this, or tuning using the structure, this alternating layers. Here we couldn't find out how to tune this. So finally, on materials, magnetism, and tuning methods in iron-based superconductors, we've seen a lot of structural and chemical varieties of the materials that are tunable, that properties can be changed using chemical substitutions, using pressure, using distortions, using the C/A ratio, as we did with the substrate. And we've seen three different types of magnetic orders from the same sort of magnetism, underlying magnetism, and with each one an interesting intertwined, interesting emergent order parameter. So altogether, we have here at hand a class of high temperature superconductors with its own particularities that are very worthwhile exploring. And thank you very much.
So thank you very much, Anna, for this wonderful talk. So now, please, if you have questions, write them in the chat or raise your hand. Cannot see question. Maybe I can start making some question. So in this potassium dope barium 1 to 2 system, you have discovered this intermediate phase. You plot here in red. Yes. So maybe I miss it, but is this phase superconducting?
Sometimes. So it is a magnetic phase. It's this magnetic pattern. And it sometimes can be superconducting. So it's the same as, okay, it's an aspect I didn't really touch upon a little bit. I said that say the orthorhombic distortion is decreased in the superconducting state, but it's still there. So there's a superconductor that's orthorhombic and magnetic. And there's also a superconductor with this sort of other magnetic order and superconductivity.
Okay.
And maybe one thing you can learn, it's a little small here, but something you can learn from these lines in the phase diagram is this line, it goes like this. So it means that the superconductor still would rather prefer the stripe magnetic order than the tetraangle, the spin charge density wave order. So it prefers the pink to the red. You can see that because the red region shrinks inside the superconducting state.
Okay.
So there's different degrees of competition between all these phases.
Okay. So then, because you have described different kinds of magnetic orders, the stripe antiferromagnetism, which is the most common, yes. And also this spin vortex crystal antiferromagnetism. So which do you think is competing more effectively with superconductivity?
Oh, that's a good question. So it's a little hard to answer that using my 1144 material, the one that I talked about, because that one does not have stripe. To answer that, you need a material that has ideally all three of them and superconductivity. Mm-hmm. And luckily we have one of these. So I skipped over that because I felt it's maybe a bit complex. Let me see, I need to go back. Sorry. Screen sharing thing because it's interesting here. So there is this one material, the sodium. Let's go here. So here I think you have all three phases. You have a stripe phase here. You have the one with the moments in and out and partially canceling, my option 2 here. And this very recently was found evidence that it's a spin vortex crystal.
Okay.
And now you can look at the superconductivity, that's the phase line down here.
Mm-hmm.
And I think what you can learn is that the C4 phase is the worst. So the option 2 is the worst. The next worst is the spin vortex crystal, and the best is still the stripe phase.
Okay.
And in this work, it was related to entropy changes and how much density of states is removed. Maybe you can look it up. There's a reference down here.
Okay.
So yeah, this is very, very impressive work and a very interesting, complex material. So many phases. I think there is a lot to be done still. Also quite intimidating, but there is a lot to be done there.
Thank you. Well, there are 2 questions in the chat. The first one is from Lenovo. Maybe Lenovo, you can unmute yourself and, or let me try to unmute. So you can ask the question yourself.
I didn't find out how to read the chat.
That can be the question. Seems not working. So Lenovo asks, are you consider vacancies in 2D materials as a distortion?
Vacancies in 2D materials. Well, there's certainly a strain field associated to them. So a local distortion. When I say distortion here, I mean an ordered one, really. Like the whole system is distorted in the same way. So I don't think it's the same thing here. When I say distortion, it means my whole material distorts in the same way. If I have a vacancy that's not ordered, that's inhomogeneous strain, inhomogeneous distortion. That's also interesting, but it's a little bit different. And I think you would not talk about phase transitions there, I think. But I'm not an expert on 2D materials.
Okay, so there is another question from Marta. Marta, maybe you can ask the question yourself.
Hi.
Hi.
Very nice talk. My question is, in the STM measurements that you showed before, the ones with the 2 areas, how do you change the pressure there? Because with the crystal, I don't know.
Yeah, good question. You can't. Let me see if I can get that. No. Yeah, there. We have to take the pressure we got. So what we have is a substrate and a sample, and the amount of pressure is really given by the mismatch and thermal expansion. The sample wants to expand, it can't, it has to follow the substrate, and that's the amount of pressure we have. What you can do, but we didn't, is choose different substrates. So you have a few discrete values you could look at. But we have not explored that systematically. So it's a little bit difficult, and yeah, so we have an estimate of how much pressure we have in that one, but we cannot easily change that amount.
Okay. Herman has a question.
Yeah, hi. Thank you very much for the nice talk. I have one question well, 2 questions actually. So when you consider the spin vortex crystal, do you think, I mean, you present this generic idea of having antiferromagnetic aura which goes away at the quantum critical point at some point. Now, do you think there is a quantum critical point associated to spin vortex? And more generically, I mean, in most of your measurements, it seems that the quantum critical point is avoided by a lot of phases, right?
Yeah.
So could you comment on that?
Yeah, okay. So the question of quantum criticality, and that's what I started with, is of course heavily studied here. In the spin vortex crystal material, there is one NMR work that claims to have found evidence for a spin vortex. It's even entitled spin vortex crystal quantum critical point. They look at magnetic fluctuations in that. But I don't think there's clear-cut evidence for a textbook-like behavior there. And there are some materials, the phosphorus doped barium 122, which I've mentioned sort of as a simple example, where there's more evidence, actually a lot of evidence for it by now. There was just a symposium yesterday on Ironbased using transport measurements, magnetotransport measurements, scaling behavior. They find a sort of scaling behavior that would come from these ideas. So yes, in these materials, at least in some of them, there's evidence for this idea. It's typically done in high magnetic fields to get rid of the superconductivity so we can look at that point, because that's one of these issues, right? We hide that special point and the superconductivity is so high we cannot really look at it. So we need to destroy superconductivity, and a standard way is to use high fields. In this case, you need 50 Tesla or so.
Okay, thank you.
Let's see, there are more questions. If not, I do have another question, because you said that the magnetic fluctuation drive nematicity. Is this also true in iron selenite? Because there the magnetic transition is farther away in the phase diagram. And
okay. Yeah, that's a good question. That's also an important point. I have not mentioned iron selenite in this talk because I felt this would get us too far. So there's this one material which has a nematic phase. Actually, I have one graph of it, so maybe that's where you picked it up. And no magnetic phase. Maybe. Okay. So my personal opinion is no. But there would be other people in the community that would say yes, or yes, maybe. I think it's the bottom right material here. So here you have a nematic phase, here you have the magnetic phase, and you already see the relation is quite different, right? It's not a precursor, it's first and then it gets suppressed, magnetism comes up. So we studied this a lot, and I would say no. I would say there's another reason for the distortion here and a different mechanism for the magnetism here. We did finally write it up in a long paper 2 years ago or so, and that's my opinion. But yeah, I have heard other people saying different things.
okay, thank you. So I cannot see further questions. So before thanking Anna and closing the session, let me mention that next Thursday we will have another interesting talk by Alberto Fernández Nieves from Universidad de Barcelona. And he will be talking about toroids, active nematics, and topological defects. So we hope that you can attend the seminar next week. With this, I want to thank Anna very much for her wonderful talk. And I thank you all for attending this seminar series. See you next week.